Hello everyone, and hello Professor J. McClelland. How are you doing?
I'm doing well. Thank you. Good morning.
Thank you for Good morning for you, and welcome to our audience today in this new episode with Hadith Tech. I hope you are really going to enjoy it with Professor J. McClelland. We really appreciate him accepting this invitation and being with us today. Thank you.
No, you're welcome. You're very welcome indeed.
So for Professor J. McClelland, he is the director of Mind and Computing Laboratory in Stanford University, and he has done a really awesome project there. And we would like to know a little him today and talk about his experience. So, would you like to tell us about your recent work and how you started your career?
Sure. when I was so I was in college 50 years ago, and I found myself. I was at Columbia University in New York City, uh, in the midst of a period when people were trying to find themselves and trying to find their role in the world in relation to government and the military and things like the Vietnam War and things like that. And I found myself asking myself the question, why do people behave the way they do? Why does this person decide they're going to take a stand against the government? And this person, really feel uncertain about which side is the right side of the question. And so started really being interested in how the human mind works. And I studied psychology at that time. I also studied neuroscience a little bit. I learned something about how the neurons in your brain encode information about the sensory experiences that you have from stimuli, mostly in vision at that time. And then when I went to graduate school, I learned about cognition. I learned about this new field at that time called cognitive psychology, where people were um, trying to understand the human mind by using computers to make simulations of human thought and using experiments to find out more about humans, how humans actually think. So that was the field that I joined as a young PhD student in 1970. Um, and, at that time, the paradigm of computation was dominated by symbolic models. Lisp um, kind of was the language of thought to many people back then. And neural networks were something that had been completely rejected. So artificial neural networks, real neural networks, nobody cared about them at all. My study of the brain had made me think, well, they must be somehow relevant, and I hadn't. So even as a PhD student, I was trying to think, well, how can I understand the human mind as something that emerges from the neural networks in our brain? So um, I've always been interested in, mind and brain. And then in the mid 70s, I got introduced to people who were using neural network models to understand cognition. And that's when I became sort of at the interface of mind, brain, and computation. Yeah. So, so that's the sort of the nutshell of what uh, who I am in terms of my scientific influences. I think about what we know about the human brain, what we learn from humans or animals about the brain, because there's lots of continuity between species. I use what we can find out from doing experiments on human subjects, and I use what we can learn from neural network models or any other model of mental processes to help me understand how people, think, and why they decide to do the things that they do, and how we can help them think better.
That's really kind of interesting research and work you have done during your PhD. But while you are doing that, was the neural network and let's say the model that we have done in the neural network that is the reason for you to getting into computing? Or let's say ask you in different question like, how did you get into computing?
Yeah. Well, so it really related to this sort of, is cognition symbolic, or is it something that arises from, a kind of a continuous dynamic process? So we think about it that at that level, the symbolic approach has it that our thoughts are discrete things like propositions, and we make step-like transitions as we solve problems. First you add two numbers and then you divide by 5 or something like that. And that, you can think of the steps of our thought processes as a series of discrete operations. But I wanted to understand our thought processes as a set of interacting elements that are sort of continually talking to each other and influencing each other in real time, so that I could understand the time that elapsed between when something is presented to you and when you get the answer in a more continuous and dynamic kind of way. And I wasn't able to do that just sitting in my armchair and thinking about it, right? I needed to have a computer program that would simulate this process for me in order to be able to then make progress thinking about it. And so, it was in the sort of 1975, 76 period when I first started to sort of try to learn how to actually write programs. And my first program was punched in cards on Fortran, and I had to take the cards to the computing center and leave them there in the evening. And then the next morning I'd get a printout back saying there was a key punch error on card 37. So I actually stopped doing that for a couple of years because it was too cumbersome and slow. And but then 2 years later, we had desktop computers suddenly in the lab that I was in at that time. And okay, now I can write a little program and run it on my desktop and see what happens. So that was how I actually got into computing. And so by 1978, I was actually a hacker.
So during that time, it was like hardest to get into let's say running programs and running simulations compared
It was
to
just something that some people coming from my field, nobody was doing it. The guy whose work was inspiring me was actually educated in an electrical engineering department, but he had gotten interested in human perception and memory. And he developed a very early, simple, now by today's standards, ridiculously simple neural network model of perceptual category formation. So just as a little example of a human psychological phenomenon, we can create sounds that range from a clear instance of, let's say, pa, or peach, okay, at the beginning of the word peach, to ba, or at the beginning of the word beach, right? So I can make a set of sounds that ranges between these two extremes. But when we hear the sounds, we always tend to hear them as though they're pretty much one end of the continuum or the other. And so he modeled this as an attractor neural network that would take anything that was inside of a category and map it into an attractor state that corresponded to that category. And that was like, yeah, that's the way it works. from my point of view, that made sense. It was a dynamic process that resulted in a cognitive, a sort of a discrete cognitive state. And we had the evidence from behavior that people did that. And then we had a computer program that would simulate that by basically having a matrix of connection weights and a vector of neuron activation values that would influence each other, and a nonlinearity that would allow them to simulate this process of settling into alternative states. And so at that time, it was to extend those ideas and capture the work that I had done and the work Dave Rumelhart was doing, trying to understand how context influences our experience that got us going using neural networks.
That's really great. That's really impressive as well. And from there, like when we introduce you as like Center for the director of the Center for Mind, Brain, and Computation and Technology. Would you like to tell us a little bit about the work you are doing there?
Yeah. So beginning with the the work that I described to you already, but subsequently through many years, it just became, I realized that I was in a psychology department. Actually, I had started out at UCSD with David Rumelhart and others there, but I ended up at Carnegie Mellon University, where computation was extremely important, and the university at Carnegie Mellon had Herbert Simon and Alan Newell, who are these godfathers of artificial intelligence, but no neuroscience. And across the road from us was the University of Pittsburgh, where they had a very strong neuroscience community. And I felt that we needed to build a bridge between these fields. We needed to integrate the neuroscience, the study of neural networks in the actual brain, with the study of computational instantiations of neural networks that Jeff Hinton, who was also at Carnegie Mellon at that time, was doing. And so I started this kind of thing when I was at Carnegie Mellon in the early 90s. I came to Stanford in 2006, so that's 16 years ago now. And I asked Stanford to help me do the same thing there, because in a similar way, the psychology department and the neuroscientists were, largely separated from each other. And there was very little computation in neuroscience at that time. Now, it's changed radically since then. It turns out that computational neuroscience is hugely important for all neuroscientists to understand their data today. And, computation is hugely important for any cognitive science to understand the human mind today. So this is a no-brainer in 2022. But back then, the neuroscientists didn't understand what an attractor was. I hope your audience does. We can talk about it if they don't. But so what I felt we needed was to create a community, and that's what this center is. It's a community of people who want to bring all three of these things together in their effort to understand. Everybody has a slightly different goal, but they know that the insights that people with slightly other goals are going to help them with their goals. Some people want to just understand how the mind works. Other people want to build prosthetic devices that allow us to see better. That's where the technology comes in. But you need the computation to understand what the piece of hardware you put in somebody's eyes is going to do, you know? So it's all about building a community where students and faculty and visitors can interact with each other around these kinds of ideas. So this is not my laboratory. This is I almost think of it as a club of people on campus who are interested in the interfaces between all of these different kinds of ways of approaching this question about intelligence and human brain function, and also how we simulate them, but also how we use them to help us think.
That's really interesting. Like, especially the idea of you like connecting to different, let's say, fields that they are not really connected at that time. Uh, for that, I think you have founded another laboratory as well, and as you have mentioned, when you were in the Center for Neural Basis and at of Cognition,
Yeah,
I think at Carnegie Mellon as well.
yeah. So that was my first sort of center, right? And that was we started that in the early 90s in Pittsburgh. It was a joint center between Carnegie Mellon and the University of Pittsburgh, which actually they're, you know, very close to each other in a certain part of Pittsburgh, Pennsylvania. And by the way, Pittsburgh, Pennsylvania is a great place for technology and computer science, of course. And I loved it there. My wife had a slightly better opportunity here in the Bay Area, so I also got a chance to come to Stanford, which is also an amazing place as well.
That's really awesome. And for at the center for mind that you are in right now, you are working for some kind of solving some kind of disorders for people and helping disadvantaged people there. Could you tell us a little bit about the research that you are leading there and how it will help disadvantaged people as well?
Sure. So I'm speaking for myself. Okay. My main goal is to figure out how to help people engage with the complicated ideas that they need to master in order to be part of the community of people who use computation and mathematics in their thinking. Okay, so a huge fraction of the world's population lives on the other side of a barrier, as far as I'm concerned, right? In terms of their ability to utilize a computer program or a mathematical argument to help them do the work they want to do, or create things that will help be of use, right? And so this creates barriers for people. Now, not everybody want to cross that barrier, right? Some people are not interested in being on the side of the line where they're contributing to technology and our understanding of how to write programs and do things like that. So, but education is the key, according to me, that allows us to reach the point where we can stand on the shoulders of those who went before us, as Newton said, and develop ideas further. And Newton's ideas turned out to totally change all of technology, and the technologies that Galileo was able to develop helped to validate Newton's ideas, and all of this kind of synergy between being able to think systematically and being able to develop technologies that allow you to amplify your observations of the world. And it's the same way in cognitive science or anything else. So my goal is to understand how we build machines that help people learn, or and in order to do that, I want to actually build machines that learn as like people do. I want to build machines that simulate the way the human mind works, so that I can then figure out how to, how experience shapes the way they think. And so that's me. But I should say that the Center for Mind, Brain, Computation, and Technology, is broad. It's my lab is, Jay McClelland's Mathematical Cognition Lab. That's what I do. But then there's other people. The center that I direct is this broader center where there are people who actually are building, artificial retinas that you could implant into somebody's eye to help them see if they had lost their vision. And so that's a different way of helping disadvantaged people.
Yeah, that's really interesting. And like, I get a question here about like when we create this kind of technology and tools, besides disadvantaged people as well, I feel like we are going to enrich the people as well for that. So we can like, let's say, have an eagle eye for someone, or we can have like a superhuman. Do you feel like this technology could lead to improve our like, let's say, skills and abilities that we have beside enabling the disadvantaged people?
Yeah. So, this is where. So I guess I believe that our mental abilities arise from our ability to engage with other people in scientific discourse, or at least to understand and profit from the discourses that people have created previously, right? So Euclidean geometry is a set of ideas, but it's also a system of thought. Like if you start from a set of propositions, you will be able to derive other true propositions by thinking. But this is very hard for people. And what I'd like to do is to be able to imagine that at some point we would have a teaching agent that would understand what it wanted to teach well enough to kind of like help somebody who was trying to work through how to prove a theorem with just the right hint, so that they would, or just the right sort of like input about what some sort of higher level way of thinking about the problem that would enable them to see how better to understand the specific problem. And so, but building agents that could do that, that is like the final frontier, right? This is, to me, if you could build a agent that would learn to think like Newton or Einstein, and then another one that could learn to teach other people to do that, then that would be awesome. Okay. I mean, there's many other things we need to do in the world: fix global warming and make sure everybody has enough to eat, and deal with diseases, etc. But this is where I would like to make my contribution anyway.
That's really interesting and awesome. And here, like to build this kind of, let's say, agents and this kind of programs and software, you as like someone from a psychologist background or psychology background, you are going to work with different like disciplines and different engineers from computer science, or let's say from electrical and electronic, as I have mentioned. How do you decide if those engineer or scientists could work together, and how this kind of work happen all together?
Yeah, well, it's very interesting. So uh, I guess, I feel like it's a challenge to figure out which person coming from an engineering background is going to turn out to be the one who fits well with this project. But and I am not being an engineer myself. I don't fully understand, the breadth of the kinds of engineers that there are and the ways in which they think. But I can tell you this, that one of the strongest PhD students I ever had was a PhD student in electrical engineering, and he came to Stanford, and I was lucky because the superstars of artificial intelligence never answered his email, but I was down there in the next rank of people who he sent an email to, and I said, "Sure, come and talk to me." And so he joined my lab, and we did a bunch of work together. Because but in his case, he really was interested in, okay, I want to understand this interface between the brain's neural networks and some kind of question about how we think as human beings using the mathematical and computational tools that I learned as an engineer. And that those kinds of scientists do exist. The guy I first learned from back in the 70s, his name was James Anderson, Jim Anderson. He was one of those people, and so is this other guy, Andrew Sachs, who is now a member of the faculty at the Gatsby Computational Neuroscience group in London, at University College London. So it's a matter of, are you interested in these things using the tools that you have that complement the ones that I have? And I've always felt like that's always been why my strength is to say, well, I have a certain set of understandings and beliefs, and you have a set of tools and understandings and beliefs that complement mine. Most of my work is collaborative, right? I find some synergy with someone else, and then something really exciting happens because we settle on a problem of shared interest that way. So it doesn't always turn out that there is a sufficient kind of match of one mind to another for the project to go forward in an exciting way. But when it does, it's been awesome, and it's been how I've mostly made progress in my career, is finding the right collaborators with complementary backgrounds.
That's really interesting. And here we have like a question about the researches that you are doing from Rawa. So it's asking like, are these researches implemented in the real world, and where do we see them? She's a biomedical engineer by herself, and she's very interested in neuroscience. So this is her background.
Uh-huh. Well, let's see. In the real world now, a lot of the PhD students at Stanford are, in some sense, in the real world, in the sense that they are not pursuing careers in academia per se after they finish their PhDs, but they're getting jobs in tech where they, for example, are developing better human-machine interfaces for use by ordinary people. So that could be one way in which you were implanted in something like the real world, because the real world anymore is a world in which everybody is using tech to help them, do the things that they do and learn, etc. Or you know, or create a yoga class or a cooking school, right? They need the tech to work for them, and you know, how does it interface with human beings who want to do those kinds of things to help them with that? So there's a huge amount of that. And one of my former PhD students who actually worked with me on how young children understand mathematical ideas now works at Apple, and she had a choice between, is she going to go to Google and work on human machine interfaces, or is she going to go to Apple and work more on understanding better how to engage people socially? And so it turns out that she has more of a social streak. And so even though she's quite competent in technology, she's more doing that sort of side of figuring out how to engineer the products that Apple sells so that they will be better at facilitating human contact rather than anything else. So those, I don't know, is that the real world? But I guess I feel like, you know, everywhere in the real world today, there are people who want to be part of the same high-tech world that of the Silicon Valley, right? And by you interviewing me or talking to other people in these kinds of fields, you allow access to that world, but you're also extending that world. So this is something that you know, people in California are really worried about the fact that everybody's leaving California. I am not. I think that people need to leave California and go all over the world and help real people all over the world, you know, join the modern world to the extent that, of course, that's of interest to them and of value to them. But so that's the way I think about the real world, I guess.
That's a really interesting way to think about the remote. Like even the way that you mentioned about people like are worried about leaving California. So from like my point of view here, it's like California is like a big magnet for those people who want to be like scientists or who want to be like awesome engineers in their life. So it's kind of like collecting all of these people in one
Yeah,
area.
yeah. But nowadays that is changing, right? So people are going to Austin, Texas. People are going to San Luis Obispo in further south in California. People are going to there's a reasonable community in Pittsburgh, Pennsylvania. London, you know, is Google and DeepMind have offices in London, and they should start one in Istanbul, you know. And the goal is these things be you know, worldwide. Engage, allow people anywhere, and so sometimes some of the major machine learning conferences, for example, one of them happened in Africa not that long ago. So and so there was this guy who was a postdoc with me for a couple of years. He just well, not, you know, about, I guess, almost a year ago now, he became the CEO of a small startup. And what they do in his company is they use artificial neural networks to recognize human faces. And he was doing this primarily because he wanted to help rescue women who'd been kidnapped and taken and sort of basically enslaved in brothels in India. And you know, they'd been forced into prostitution. So people would go into these brothels with hidden cameras and get pictures of the young girls, and then if they had pictures from their family of who these girls were, they were able to match them up and then sometimes rescue the girls. And there's all kinds of uses for these kinds of technologies in India, in any place in the world. So his startup is doing things that many different applications, want to use, and that's just another kind of example of how you get into the real world.
That's an interesting example. And as you mentioned, like the DeepMind and Google work, you are working with them as well. Um, I would like to ask, like, how, as you as psychologist, like contributing directly to the science there or to the computer engineering there.
Right. My role at Google is, at DeepMind, is really to say, listen, I think that your current sort of artificial agents are limited in this kind of a way. And I want to get you guys to start thinking about how you overcome that kind of limitation.
Yeah.
So maybe I can give a little bit of an example of this. The today, many people are deeply fascinated by transformer-based artificial neural network systems like GPT-3 and BERT. Is your audience familiar with these ideas? These,
I think so.
yeah.
Or if you want, we can explain
Well,
them.
so let me just say a little bit about. Let's just take GPT-3. Okay, so GPT-3 is trained on this massive corpus of, a trillion words of text, using this huge neural network that has trillions of parameters in it. And then what is it trained to do? It's trained to predict the next word in text from a past stream of text. Okay, so that's all it ever does, is it takes a text starting from the beginning of some document and then predicts the next word after that, and then another document starts and it keeps predicting, and so on. And this is something that is easy to automate. You gather all this text together, okay, and then all you do is just predict the next word, right? And that you can automate that pretty easily. But it's really limited in that, human beings, we do learn by processing text, but we also learn by being immersed in the physical world, and having objects in front of us that other people are talking with us about, or by actually carrying on conversations with other people as we solve problems. And it's sort of, so how do we build a learning system that learns in a embodied physical environment, interacting with objects in the world and interacting with other people through sort of discourse about the objects and what the goals of manipulating them might be, and all of those kinds of things. So this is, if you look at the things that I've written recently, they've all been sort of like, how do we encourage more of that? Okay, I had a paper in the proceedings of the National Academy of Sciences about building an integrated understanding system, something that has the characteristics that I was describing. And that's a paper in collaboration with a Google, DeepMind, and a couple of other computational linguists and computational intelligence researchers, and myself, a cognitive scientist. So that's the kind of role I have. I'm bringing this sort of attitude of integrating multiple sources of information and engaging in understanding through discourse, the same way we are now, right? You're asking me questions, I'm sharing thoughts um, about how to, about the answers to these questions that are, and then other people are asking us questions. So for some in the audience, this is a little bit more like GPT-3, but for me, learning is all about interacting with the world, changing the world, doing experiments with it, talking to other people who may be smarter than me and getting their ideas about how to solve the problem and so on. So that's what I want to do. I want to help DeepMind, create and other, because I'm sort of very into the open publication model that DeepMind primarily, explores, right? Getting their ideas out there.
That's really interesting. Here, like when you mentioned the GPT-3, I just remembered recent research talking about like when neural network, or let's say this kind of agents learn from Wikipedia or this kind of, let's say, uh, resources, it have a better attribute or a better information rather than learning from just a social media, and it become like giving a different idea there.
Yeah. So, I mean, I'm not sure I think social media is what I would focus on, but I the things that um, I find super important are the interactions that um, we have in in the well, I guess social media is important for many people in the sense that they spend so much of their time in it, right? But early in life, before the age of 3 or 4, we're actually immersed in an environment that is mostly determined by our parents, and maybe we're in some small daycare setting, for example, where we're with other children during the day or something while our parents work. But it's a real immersion situation as opposed to a sort of one mediated by technology. And the things that go on in those settings are, I think, extremely formative for how it is that a mind will develop. For me, my mother was studying philosophy as an undergraduate when I was born, and she, in order to keep me quiet as a colicky baby, she would read Aristotle to me so that I would calm down. But presumably, this may be a slight exaggeration, but I sort of think that my interest in how people think is actually sort of partly stimulated by the fact that my mother was so interested in those things and was talking to me about them as an infant, right? So
Yeah.
so this is what I'm so interested in, how the early formative processes that happen in early life sort of shape who it is that we turn out to be. Like Mozart turned out to be one of the most amazing composers ever because he was born to be the fourth performer in the family string quartet, right? And um, uh, I think that there's a huge amount of this sort of contextual influences on who we are that are set in very early in our lives, and then it becomes so much a fabric of our being that we think it's like innate or something, but it's really this immersion in early experience that shapes who we are. So this is what I want to do. I want to build systems that immerse agents in experiences that will structure their minds in order to make them um, uh, contribute better and be more effective for their own goals.
That's really interesting. And even though the story of like you as an infant when your mother was talking with you is like showing how much important environment for people to like, let's say, who are becoming scientists and who are becoming having a great position in their life. Uh, Here I get like a question for you is like a lot of people who see you as like a role model or who see you as a hero. How do you say, what do you advise them to do and suggest them to do in their life?
Well, the first thing that I always say in answer to a question like that is the things that have propelled me forward have always come from something inside of me that thought that that was interesting. Okay. And so what the basic answer that I would give to this is, so like, look inside yourself and see what's telling you is the opening for you, right? Where is that opening? So I really feel very, very much like this was a very central element for me in that period that I was describing of the 1970s, when I went to graduate school in cognitive psychology, and I could have easily followed the then sort of standard path of using symbolic cognitive modeling, or just doing behavioral experiments, which is what I had mostly done in graduate school because that was just the context I was in. But coming out of graduate school, I wanted to understand the answer to these questions. How is it that, I can have a sort of a underlyingly continuous system that learns and kind of thinks in ways that, ultimately may be very symbolic and abstract, right? That's able to formulate theorems in geometry or something else, for example. And the idea that I could bring the brain together with that enterprise was something that, very few other people were doing, but this motivates me. And I think that in a way, this is really central to almost everyone who's been super successful. Steve Jobs wanted to build machines that people could actually use, right? Yeah. That's so the Mac, rather than the TRS-80 or something, which was only for hackers. I was happy to be a hacker, right? I didn't want to help other people use the machine. I wanted to use it myself, but that other vision was what created Apple. And, Demis Hassabis created DeepMind with others because he really thought it was time for us to get substantial resources behind the goal of building machines that integrate insights from neuroscience. He actually has a PhD in cognitive neuroscience, by the way, not a PhD, but his well, I don't know. I think he did a postdoc and a PhD in those areas before starting DeepMind, having come from a very computational earlier background. So I'm not sure about all the details, but he's definitely one of these people at the interfaces between all these ideas as well. Okay, so this is what I would say to anybody.
Just follow what you like and what you are interested in.
Well, where you think you'll be able to do something that will advance the state of the art in a way that makes sense to you. I mean, this is what, I don't know. Advancing the state of the art per se shouldn't be the goal, right? But it's like it does interest you, but it also, is a place where there's an opening. And I think that's it. And I guess, sometimes there has to be a lucky synergy there, that you are interested and there's an opening there. Yeah. And some people won't necessarily find that, but there's so many little niches where people can make contributions that I think it's, so many amazing startups out there that are making contact with some need or other that maybe just a sub part of the world cares about. That, I think there's so many opportunities for people to find those things nowadays.
That's really awesome. And for this, like, how do you see the future of the computing and psychology?
Um, uh, I think um, the field of psychological research um, does have two kinds of people in it today. They're the people who are, you know, comfortable with computation, and the people who are not. And I think that, this once we get to be adults, we really are one kind of person or another in this respect. But I don't believe at all that this has anything to do with, like, our genes or something like that, right? I think that um, being able to at least have some appreciation for quantitative and computational ideas is a prerequisite for um, engaging fully. And I don't mean this as something that people should take as criticism if they don't do it, because they can collaborate with others and others can come and, assist them in this respect. So, there are ways around this, but I think that what I'm expecting, let's say, is that it'll become more natural somehow for a larger, the vast majority of learners coming through our school systems to have at least a certain comfort level with how the computations are really occurring and what the what the back end is actually like, which is uh, going to then contribute to their ability to make further contributions to understanding the behavior itself that fascinated them so much. So somebody might be interested in why people get emotional when people say things that push their buttons, right? And how do we help people regulate their emotion? That is a legitimate psychological question, and we have a group of people in my department who are affective scientists. That's what they study. They study these emotional issues and how we can regulate our emotions. And what I sort of hope for is that a kind of understanding of maybe the brain's computational mechanisms that lead to those kinds of things, or how to build artificial systems that simulate those kinds of things, will become more central to that part of psychology, as well as now being so central to the part of psychology where we think about human cognition. So you can't study human cognition anymore in a psychology department without being well versed in computation. It's just no longer at all possible. But it is still possible in many other areas of psychology. And again, I don't mean to say that people haven't made contributions. They have made profound contributions without being computational. But I think that in the future, those the ability to extend and utilize those contributions will be facilitated by gaining more engagement with the computational ideas. And it used to be thought that being bilingual was a problem because it competed in your mind for space that your primary language would use if you had to learn a second language. And maybe there's a small degree of truth to that, but really, for people in many parts of the world, if you aren't bilingual now, you're missing out on a huge thing, right? So it's sort of natural that everybody in like Switzerland, I mean, it was true in Switzerland 60 years ago. Now it's true all over the world that you need to be bilingual, right? Or multilingual. And so why can't we all be literate in computer science as well as, and now everybody has to read, right? That's the thing. Everybody agrees on that. Well, why can't we all have a certain degree of greater literacy that in computational and quantitative thinking that will, in the same way, allow everyone to have access the same way reading does or bilingualism does. That's sort of my thought about that.
That's really interesting thought, especially the like bilingual and the multilingual one, because like as you mentioned, like 20 years ago, like or 30 years ago, when you are bilingual, you are just like an awesome person, and everyone will look for you to be like a role model. But like right now, it's like it's a unusual thing for people.
Yeah. Well, I mean, certainly in the world that I travel in, I, of course, am not, right? The only language I speak is English, really. And I was obviously English is a privileged language. I totally appreciate and understand that. Um, and so, it's just the main thing I'm trying to say is that um, having encouraging the attitude that we can learn anything, and that acquiring sort of computational and mathematical, and I keep emphasizing the mathematical side. Computer science does involve a degree of mathematics, which um, goes hand in hand with developing new algorithms and understanding, what is a better algorithm than another, and so on. And so, but anyway, it's not like I'm saying, well, if you don't feel like you're as good at that as somebody else, you can't make a contribution. What I'm saying instead is, if you can um, gain more engagement with those kinds of ideas, it will increase your competencies and your ability to contribute. So it's on the plus side rather than sort of, yeah. Anyway, so seems like we've run out of time here. So
Yeah, we are out of time, and we really thank you for your time, and really appreciate your time and your talk here. It was really interesting and teaching, or let's say thoughtful for that. Uh, and thank you for everything you do.
you're welcome. Thank you.
Thank you.